Indeed, I'm Ben, and I am the last obstacle between you and lunch. We'll start that way. But yes, we will be talking more about the mysteries of the Pacific Northwest as it relates to the post-fire environment. First things first, I want to give a shout out. I'm the lousy messenger for a bunch of great people here. So I'll give a shout out to David DeSouza, a PhD student at OSU. Marin Sanders, who's here, has done some awesome work with mapping. Right there, Marin, raise your hand. Francis, who's helped guide us in this post-fire environment. And Bill Burns from Dogami, who has the best name for studying the post-fire environment. Let's just be real, honestly, perfect name. So the Northwest, especially the western part of it, is kind of a mystery. We have mixed severity fires over these landscapes, and they've shaped the landscape to some level over geologic timescales. But recently, as Ian showed in his previous talk, 2020 was quite a year. We had a lot of fire, very large areas that burned, and we're all waiting for the debris flows. But some of them are delayed, and it's kind of a mystery why. What we see is that kind of the legacy of wildfire from the landslide perspective is somewhat poorly constrained. We're not really sure what controls the timing of these, and what we suspect is perhaps, maybe, the mechanisms are slightly different than what we see in the drier climates of the US. Perhaps there's less ravel. Perhaps there's more infiltration-driven failures. Perhaps it's a function of the sediment in the channels, right? So what we've been focusing on is various facets, but really what I'll talk about today is more the side of what might control those delayed failures. So it's a work in progress. I feel like a black sheep. There's been a lot of talk about water, but I'm going to sweep that under the rug and pretend like water doesn't matter at all here. But we do have some monitoring, actually with some great guidance from Kate as to monitoring rainfall, and snow melt is a big question here. But what I'll focus on more is kind of the quantitative analysis of the rates of landsliding and debris flows that we see from a case study in the Eagle Creek wildfire area, as well as sampling and testing of root strength in burned areas, and how we use that to parameterize models for slope stability. For example, shallow landslides that might be one driver of sediment loading and triggering debris flows. Our sites are meant to capture a span of time. So Eagle Creek is one fire we look at in 2017. Holiday Farm in 2020, one of the Labor Day fires, and Cedar Creek in 2022 are sites of interest. These are all national forests, so they have maybe different management practices than private forest lands. For Eagle Creek, we'll start with that, looking at differencing of LIDAR and the events that we see there. And the last thing we'll talk about is what I do best, dig myself into a hole, but in this case to actually extract some roots and test how that strength changes over time. So we'll start with mapping, and Bill Burns led a lot of this effort here. We were fortunate enough to have multiple epochs of LIDAR in the Eagle Creek wildfire area in 2017 at the Columbia River Gorge, including data sets that were prior to the fire itself. So there's a couple of different epochs we see here. They don't all span the same area, but they do represent the most active zones for debris flows and wildfires, even in the pre-fire environment. We had some protocols and standards for mapping these events and looking at the volumes associated with them. And the data sets we're talking about start in 2009. That was our first LIDAR collect. And between 2009 and 2018, which spans the 2017 Eagle Creek fire, we had two storms of considerable size, let's say. Mainly rain on snow events, which seemed to be a big control, certainly in the western part of the Cascades. In 2018, we collected LIDAR, and in 2021, there was another LIDAR collection, as well as in 2022, which had 2 and 1 large rain on snow event storms between them. LIDAR is a pretty amazing tool. Everybody makes it look easy, but it's actually extremely frustrating when you difference it. It always ends up being that the North Hill slopes are building up for some reason, the other ones are dropping down. Yeah, it's frustrating. But there are means, if you know a real LIDAR geek, to kind of constrain that error a little bit and get your tolerances and uncertainties here. So we were fortunate enough to do that, where you might see that red is erosion and blue is deposition. So okay, here's the map. This shows the outline of the area of the Eagle Creek fire. And this represents the events we saw in 2009 to 2018 in that awesome hot pink. It's a little tough to see, but they're there. Those are debris flow events that occurred during this 9-year epoch. Generally, we saw about 48 events during this period, and it's tough to isolate whether there's a coalescence of these, but we see about 20 shallow landslides and about 30 debris flows over this period, averaging out to about 5.5 events per year. Now, during this period, we had several large storms, rain on snow events again, and what you're seeing there is kind of the best guess based on rain gauges and snow water equivalent from nearby, well, not as nearby as we'd like, snowtails, but the actual equivalent water that we're expecting during these storms. And one big quandary, one of the big mysteries is, how the heck do you even define a storm in a place where I don't see the sun for 4 months a year, right? It's drizzling. When does it start? When does it stop? This is a big question and really makes it a different problem than the drier sides of the hills. In 2018 to 2021, this is a 3-year epoch, a slightly smaller area, we see 241 events. That's about a 5-fold increase for an approximately same area, 89 shallow landslides, 152 debris flows, and about a 16-fold increase in the events happening here. Now, the Columbia River Gorge is somewhat of an upper bound for the West Cascades. It's not necessarily representative of all of the Cascades, but represents an extreme end of what we'd expect for landslide events. During this period, we had several large storms here, especially in 2021, which yielded very large debris flows, some of which actually affected the infrastructure nearby, and we're still dealing with the aftermath. 2021 to 2022, 74 events. You might notice there's a smaller area, and if your question is about that, it's because that's all we could afford. Unfortunately, that's the lame answer. But what we did do is look at one of the areas where we saw a lot more action. And so still 74 events per year on average, and still sustained high rates of shallow landslides and debris flows despite the smaller area of observation. So looking at this as an overall kind of trend, what we see is, at least for the Columbia River Gorge as a bellwether, at least a case study, we see that there is an uptick in shallow landslides and debris flows following wildfire, right? The biggest events we've seen happened in 2021 and 2022, and there wasn't that much action just following the fire, which is kind of the thing that we're trying to figure out. Why is this? Why the delay? Why the lag? What's controlling this delay in time and where we actually see some of these post-fire mass wasting events? What we see is generally the highest rates of shallow landslides are sustained about 4 or 5 years after it, the fire. And what we suspect is that there's a couple things that could affect this. One, erosion, maybe overall not so much ravel, but just generalized erosion, loads channels for later debris flows. It's something we see in lots of places. And of course, these in-channel failures can yield large debris flows that bulk with sufficient sediment if it occurs. We also know that shallow landslides themselves can trigger debris flows and load those channels with sediment. So what we see is that there is a sustained rate of debris flows that we've mapped, at least, as shallow landslide initiated, and it actually seems to be increasing over time. One thing to consider, at least from a mechanical perspective, I'm a solid mechanics geek, is that, well, if you have very brittle behavior for strength of a shallow landslide, for example, when it fails, you'll have a rapid release of material and it'll have mobility. So we suspect that perhaps, maybe, the vegetation is one side of this thing, the roots themselves. So I'll give a shout out to Marin here. She had a great poster yesterday and did a much better job than me explaining this, but I'll do my best. Marin here did a closer look at kind of the sequence of events in some specific catchments, named debris flow catchments. You know they're bad because they have names, right? It's always an issue. So we have Levens to the left, Tumult to the right. And we see that there's events that stem in orange and purple for 2021 and 2018 respectively, right? So what we see is Levens Creek to the left was pretty burned. That's a soil burn severity map, and we see that there's numerous in-channel failures and shallow landslides stemming from the danger zone in red, right? We see that. Quite a few events occurring during this time period. Tumult actually had some of their events initiate from a completely unburned region. We shouldn't forget that, well, you know, fire certainly affects the landscape, but you still need a storm, right? You still need a storm. So we see that in Tumult, while there are some events that stem from fire, from burned areas, a lot of them actually stem from unburned areas. Now, I love this catchment name, Rock of Ages. It sounds like a great band name. And frankly, it's a smaller catchment that was very burned as well, but had minimal post-fire response, which is kind of curious. Similar morphology to Levens and similar burn severity. Well, the reason is possibly that the pipes were cleared prior to the fire. There was large debris flows that occurred in the period prior to wildfire, and maybe there wasn't as much sediment to yield large mobile debris flows. And so part of it, one big question, is what are those initial conditions prior to fire? I think it's a big question. So the same storms in 2021 and 2022 produced debris flows. burned and unburned areas. At Rock of Ages, these are averaged erosion rates from these places. Pre-fire, we saw quite a bit of erosion overall, representing a lot of material leaving this catchment. And post-fire, quite a bit less. The pipes are clean. In Levens and Tumult, the catchments that yielded very large debris flows post-fire and burned and relatively unburned conditions had very little loss of material during the period between 2009 and 2018, which suggests materials loading there, and that could yield more material for a debris flow. And Levens itself had very large erosion post-fire, suggesting that eventually there was enough sediment, or I should use the word fuel perhaps, to yield a big debris flow. So, some observations from this that kind of guided some of our other research facets here. We see, maybe expected, maybe not, but that the rates of shallow landslides and debris flows following wildfire, they're elevated, they're amplified following fire, but there seems to be a delay in it. Burned and unburned catchments will yield these events. Fire might affect the magnitude or the rate of loading of sediment in these channels and recruitment. But if you have a pretty clean channel, you might see a little less action, or it might take a longer time for this. And the shallow landslide rates that we see sustained over a period suggest that there is some capacitor that controls this delay on failure, at least for this site. So we think of vegetation as one potential control. So I'll put a plug in for David here. David has dug 28 test pits, 900 roots, brought them back to lab. It's good to be young, I'll tell you that much. I'm just sore thinking about it. And what you see on the left is a tensile device that allows us to actually measure the root strength and its displacement and give us effectively what's called a stress strain curve to get an idea how stretchy and how strong these roots are, right, at different sizes. So what we've done is taken these various fires that burned at different times to represent different time frames of post-fire root strength, right? Diameters going from 1 millimeter to 30 millimeters, and some pretty big capacities. So I'll take a break, I'll breathe, and I'll give you a pop quiz because I'm missing class today anyways. I have to do this somehow. How much force do you think you need to break a 1-inch root? Price is Right rules, don't overestimate it. Well, about 660 pounds, 300 kilograms. It's not a trivial amount of load. So I Googled what that is because everybody has different opinions on units. A small grizzly bear, I didn't know you had medium grand pianos. I didn't know that was a thing. A blacksmith's anvil, and proving the internet's a real weird place, 2,500 hamburger patties. Yes. So we looked at densities as well with depth, right? Naturally, in coniferous forests, the roots tend to be in the upper meter or half meter or so, right? I know the colors aren't great here, but black is unburned. I don't know why we chose that color scheme, you can blame me, but the colorful color schemes here represent post-fire conditions. What we see is that burned test pits had less roots, specifically smaller roots in that upper zone here, so the density decreased. What we saw also is that the larger roots tended to remain. The densities, as you can see here, start at about 79 roots per meter for our unburned sites that span all of these places, by the way, as well as 43, 53, and 47, kind of a plateau in root density over time. The classic way of defining how strong roots are, well, is saying, here's my diameter roots I dug out of the ground, and here are their respective strengths. So y-axis, look at the left plot perhaps, a little less noisy. Y-axis is strength, x-axis is diameter, and naturally as the diameter increases, the force it takes to break these increase. We see as we go 1 year post-fire, well, that curve didn't change much. I'll flip back, there. Didn't change much, and that's kind of curious. 2 to 3 years after fire, however, we start to see a drop, a significant drop, and 5 to 6, even further. So what we see when we plot all these diameter strength relationships, as you can see here, unburned and shortly after fire, they're not all that different. There's a rapid decrease in strength thereafter, though. So it begs a question, and really one I need to talk to ecologists more about. Are burned trees alive? Maybe they're kind of hanging on and they take a little while to go. Are they dead? Perhaps. They're undead. I'm not entirely sure, right? But something weird's happening in that first year. So some potential mechanisms for this include delayed mortality, right? Sometimes trees actually take a little while to decay, and perhaps this stunts decay. That might be one part of it, but it's tough to say. But if we look at the overall tensile strength shown in this table here, and that's your tensile strength, we see that there is a drop and a sustained plateau thereafter. And we think that to some level it owes to lower root density, the loss of small roots. Small roots actually die and regenerate frequently over time. And if the trees are dying or dead, well, they're not doing that anymore, or at least it takes a little while for the understory to come back and actually start to give you those small roots. Another big question, I mean, the fire ecology talk and some of the great conversations we had at this conference make me think that, well, what's actually coming back after the fire? I can tell you from painful experience, it's a lot of spiky things, a lot of them, frankly, but it might take a while for those roots to come back in terms of trees. One thing we explore a bit is, well, what we've often done when we try to parameterize how roots might stabilize slopes is we make the assumption that the roots all break at once. But the fact is, the small roots and the big roots, they might act differently. They might mobilize strength differently. So there's a story to tell about the ductility of these systems and how brittle root systems might be following fire. So consider this. Not all the roots break at once. There's a lot of small roots, and maybe in kind of a simplistic way, they're stiff. There's very few big roots, but they're a little more extensible. They don't necessarily all break at once. So we can use some interesting models that, at least the concepts of some models like the fiber bundle model, that allow us to look at root strength versus displacement and how they change. And at least start to kind of nibble at, well, what is the peak strength? And how does that relate to ductility or brittleness of these systems? And why is that important, you might ask? It's a fair question. If you pick up a stick that's dead and you try to break it, well, it'll break with very little displacement, right? Very little bending. But a live stick, one that you've just taken from a tree, will bend a lot. Well, that brittleness will actually suggest, well, what is the likelihood for you to have wind throw, for example, if a tree's blowing in the wind? If you start to have shear or instability in some location, you might break the roots locally, but not completely break them down slope. But the more brittle it is, the more likely you are to break them all very rapidly. So it matters. This is a busy page, but bear with me. The left plot shows us our load on the y-axis versus displacement behavior averaged out over all the root systems here. Kind of the greenish blue, the highest curve there, represents unburned conditions. As we go to Cedar Creek, light green, and then Holiday Farm orange, and Eagle Creek in dark red, we see a persistent drop and kind of plateau in the peak strength, but more notably, the sustained displacements in which you can actually manage to have tensile strength. So there's a brittleness here. There's a quick drop off in root strength we see over time. A quick note, you can kind of use a simple estimate of saying that generally we're going to overestimate the overall root strength by a factor of 2 if you don't consider progressive breakage. And that might be a little trick you can use to parameterize your models. But we can look at the dead roots. That's the central plot. And Cedar Creek, understandably, since it's a fresh fire, has the highest strength from the dead roots themselves, and we have the recovery roots as well. So we can look at these and start to think about things over time. That's the goal, right? Is what is recovery? What is changing over time? On the left top plot, I know it's busy, but all those scattered points, it's noisy, this is real data, where we have each test pit's overall root strength. There is a general decline for all the roots, but in the central plot, you'll see that behavior per test pit for all the dead roots, and the decline is pretty distinct. What we can do is use some of the classical tricks where we say, all right, here's all my roots. Here's the dead root behavior over time. The difference must represent recovery. And if so, I can get a function for recovery roots, and I can get a function for dying roots. And if I add them together, all of a sudden I'll end up with the magical plot right there in the bottom left, which shows us, well, what is that overall root behavior like over time, right? So we consider this behavior and we see that there's kind of this weak spot, this low point. We lose about half our strength, and it happens to occur in about the magical 3 to 5 year time frame. So we can look at this a bunch of ways, but here's just my poor drawing of that. I did my best to draw in Excel. This took me at least 3 hours. It was really good use of my time. But what we see is that we have these two superposed curves, right? And we have this overall root strength. When we parameterize a slope stability model, we need to add some strength. Usually that's friction or cohesion. Now, we often add roots as a root cohesion. And I'll tell you, as a geotechnical engineer, everybody has an opinion about root cohesion. I have at least 4 of them, right? There's a lot of, I could debate all day about it, but I won't subject you to that. But understand, there's debate about that. But for the medium root conditions we see. Generally, strength is at its lowest in that 3 to 5 year time frame. If you want to look at kind of recovery, and again, there's error bars on this, but if you want to look at recovery, about 12 years for 50% strength recovery, 25 years for 90%. So you might ask, some of you who are familiar with the root literature might say, hey, that looks familiar. Well, you're absolutely right. The closest analog we can really think of is, well, timber harvest, right? We have active forest industry in Oregon, and there's been quite a bit of research looking at shallow landslides in particular following timber harvest and the replanting techniques. So one of the references we look at, we compare these kind of strength relationships here that are idealized, and what we see is that there's a relatively similar shape. Sure, there might be a slightly different decrease. There might be a different time frame when you're in the danger zone, right? But they're not too different. And that suggests that perhaps timber harvest relationships aren't a bad conservative assumption at the very least, right? But there are large uncertainties. And I really, again, think back to that fire ecology talk yesterday. Replanting versus early cereal vegetation are two huge differences between managed lands and say, managed maybe is not the right word, ecological forestry that you'd see on national forests. These are on national forest after all. There's the hydrological effects, which is the elephant in the room. Please don't pick on me regarding that. There's definitely water as an element here. But the mechanical controls are an element here. So we can plug this into the simplest type of slope stability modeling, and just bear with me here, but we'll say it's the infinite slope, a slab that basically just takes in thickness and the hill slope angle and says, will it stay or will it go? So we have an equation for something called a factor of safety that says, well, what's my level of stability? Greater than 1, I'm stable. Less than 1, you're going to have a bad day. And so this plot here, the y-axis shows the slope of that slab. The x-axis shows the saturation ratio. What proportion of that hill slope is saturated with water, right? And this whole green zone represents, for this set of conditions, the area that would not fail under unburned conditions, but does under burned conditions, at least at different time frames. And I'll conceptualize it this way. We have a reduction in root cohesion. As it reduces, maybe more marginally stable slopes will be the first to fail, but there is a time frame where we'll see failure in kind of areas that are more gentle, or they fail with less saturation. Again, you need a storm to cause failure. So if you consider that green dot as our starting point, it wouldn't fail at that point without fire, without loss of this strength. Well, we can say that we can start to see failure at 2 years or 4 years under lower levels of saturation. It takes a little bit less of a storm to cause failure for the same hill slope is the idea here. And it just depends when you get the storm to some level. So to summarize, root strength may be as expected, but poorly quantified. It decays. It decays after a wildfire. Generally, we see there's an exchange in the decay of coniferous roots and what's burned, but as well as the regrowth of vegetation, which can be lots of things. It can be seedlings, it can be the nasty devil's club, which is aptly named, but they all have roots. They do. And it can result in the loss of root strength. Unburned root systems are more ductile than the burned ones. Those big roots take a while to die, but they are not very ductile. They're brittle. They're brittle root systems. And we see that there's kind of this danger zone in time that happens approximately, at least from what we see, about 3 to 5 years following wildfire. Maybe there's a recovery thereafter, but the uncertainties stem from what grows back. And that leaves a lot of open, great questions that I don't know if I can answer them, but I'd love to chat about them. That recovery, we put numbers on it. It's a model, but we have some numbers, and it's 10 to 25 years for about a 50 to 90% regain in strength. This data represents a snapshot of fires, all of which are different. Vegetation and climate regimes are all different, but it gives us something to give us an idea of, well, what's the reasonable numbers? What are the bounds on this problem? And there's a lot of research to be done, looking at different management practices, whatever it might be. But really, in the end, that loss of root strength can enable at least shallow landslides in the areas that were already metastable, marginally stable to begin with, right? At the fringes, that's what we're seeing. And these shallow landslides, they can trigger debris flows, especially potentially with brittle roots, but more so, they can load channels, right? This is another source of sediment. And having sediment in those channels is what allows you to have bulking and very mobile debris flows to begin with. So with that said, thank you for your time. Appreciate it.